So, do you want me to start, or is Vijay Bhaskar is okay?
He will join.
Okay. Do you want me to wait?
Sir, Harina, sir.
Yeah.
You can start, sir. Why? Because HOD sir is now, I think maybe he went outside. Maybe within 5 or 10 minutes it will take time.
Okay.
And we will start that.
Yeah,
We have time to just start, right? Otherwise.
Yes, sir. You can start. You can start. There is no problem.
Okay. So, Uma madam is available.
Madam.
Yes, sir.
Let's start, madam.
Okay. Good afternoon to everyone. I welcome you all for the last session of the 1-week international FDP on research challenges in mechanical engineering, conducted by Department of Mechanical Engineering of Sri Venkateswara College of Engineering and Technology, Chittoor. It's my great honor to introduce our today's guest, Mr. Lepakshi C. Medasani Garu, Technical Director, New York City Special Inspection Agency, Project Manager, Capital Improvement Projects. He has completed his master's from the City College of New York, USA, and bachelor's from JNTU. Now, I invite our today's guest of this session, Mr. Lepakshi C. Medasani Garu, to give lecture on HVAC design. We welcome you, sir.
Thank you so much. Thanks so much, ma'am. Well, good day, everyone, and hope you are doing great. My name is Lepakshi Medasani, and I've been working as a project manager for capital improvement projects for the past 11 years. And I'm also technical director for New York City Special Inspection Agency, and I'm licensed professional engineer in the state of New York as well. So let's jump in. And then today what I'm going to do is I'm going to present a brief overview of HVAC design. And it's a very vast topic, and as we have very limited time, I would say like an hour or so. So what I'm going to do is I'm going to just briefly go over of what are the systems that are involved in HVAC stuff, and the later towards the session. So I'm gonna concentrate more on the boiler stuff and all those things. Okay, let's jump in. So let me start sharing my screen so that you can see what I'm telling and all that stuff as well. Okay. So
Serum, sir.
Could you
now we can, sir.
Now you can do it.
Okay, perfect.
Now you can do, sir.
Perfect. So you all see me? Just see my screen, right?
Yeah. Now we can.
Yes, sir. Yes, sir. Yes,
sir. Perfect. So today our topic is going to be on HVAC design. So pretty much I'll concentrate more on the boiler plants.
Sorry for disturb. Can you make it presentation mode?
Pardon me?
So wider the screen. So go for the presentation mode.
Yeah, okay.
So bottom right side, you can see that. So bottom right side, you can see that the left one. The next, again, right to that one, The another one. Yeah, that.
Okay, got it. Sorry, my bad.
Yeah, okay.
All right, so let's discuss about HVAC stuff. So what exactly is a HVAC system? So HVAC is just a short form of heating, ventilation, and air conditioning. Normally people call it as HVAC or HVAC systems. I prefer the HVAC stuff. So what exactly is this thing? So these systems are being designed to achieve the environmental requirements of the comfort of the occupants or persons, and it's a process. So HVAC systems, these systems, they'll be used in different sectors, such as industrial, commercial, residential, and institutional buildings too. So we're not going to concentrate these systems where they are going to applicable and all that stuff. I'm going to pretty much go straight forward on industrial commercial applications only. So these systems work basically on the principles of heat transfer. What are the objectives of HVAC systems? As I said, HVAC is the heating, ventilation, air conditioning, refrigeration, life safety, controls, and energy consumption. Life safety is the first and foremost goal of these HVAC systems. Again, HVAC is just processing of the air. So human comfort comes into play. So temperature, humidity, air velocity, minimum ventilation, indoor air quality, noise and vibration. So all these factors, they depends upon the human comfort. And if you have proper comfort and all that stuff, the productivity of the humans will be, I would say, more. So, and you have the equipment and process requirements, building and material preservations. So these are all the objectives of HVAC system. Before you're going to design any HVAC system, these are the important points that you got to consider. Like for instance, what would be the comfort temperature of the persons who are in that particular building or so? The comfort, human comfort depends upon individually. It's a preference. For instance, I prefer a certain temperature and I'll feel comfortable at 75 degrees Fahrenheit. And you might be feel comfortable at 78. So it's not like you go to each and every person, what is your comfort and all that stuff. You don't go that way. So there are pretty much some standards, like the ASHRAE, it developed some standards for the comfort zone. What would be the temperatures required for the human comfort and all that stuff, which we're going to discuss later down in the session. Now, on the today's session, what I'm going to do is I'm going to start with the basics. And not that like you don't know about the basics and all that stuff, it's just to refresh your memory so that you and me will be on the same page, as this is the fast-paced session. So I'm going to put like a lot of information over here. I don't want you to stick to, oh, what is this, what is that? I don't want you to get confused with all those things. So I'm going to just refresh your memory. You all knew all these things, but I'm just saying it again and again. And that's my first thing. And after that, we're going to discuss about what are the different HVAC systems are there. Not each and everything, but most of the stuff what we are going to use in the common applications. And the next step would be calculating heating and cooling loads. How are you going to calculate heating and cooling loads? We're going to discuss that thing. And after that, I'm going to discuss on air distribution, which means like dealing with air handling units, which are AHUs and rooftop units, RTUs, and ductwork, etc., etc. And sizing of the duct, that's the most important thing. How you going to size the duct? So you're going to discuss on that stuff also. And the boiler plant, this is what I'm going to put more concentration today on this session because it's quite new for the people back home as well. And normally we don't deal with this kind of stuff. The rest of the things you might already heard somewhere and all that stuff, but boiler plant used for commercial heating applications is something new that we're going to discuss in this session today. And lastly, climate control. So that's what it's going to happen today in this session. And hopefully I'm going to give some insight on all these things, and hopefully you will learn something new today. And just be careful on the units and all that stuff. So all the units that I'm going to present in sessions, it's going to be on English pound system, which is English system, inch and pound IP system, not ASA system or MKS system. Please be aware of that, okay? Thank you. Now, let's jump on to principles of heat transfer. What exactly is the heat? Heat is just a form of energy, and each and every object on Earth contains heat energy. It has both quantity and intensity. Each and every object, for instance, take myself, I'll be having certain amount of energy. So in the form of heat, I mean to say that my body basal temperature is 98 degrees Fahrenheit. So even if I'm sitting over here, there is some sort of heat transfer process going on to the environment around me. So it's just a heat transfer going on. It depends upon what the room temperature is right now over here. If the room temperature is higher than my body temperature, then the heat is going to come into my body from the atmosphere. That's how it is. It's just a heat exchanger. Now, how are you going to measure the heat? There are some units, which is a British thermal unit, which is called BTU, which means like it is the amount of heat energy needed to raise the temperature of 1 pound of water by 1 degree Fahrenheit. That is the amount of 1 BTU. Now, let's talk about the methods of heat transfer. You all know about how the heat transfer is going to take place, which is conduction, convection, and radiation. So those are 3 modes of heat transfer normally we talk about in our sessions also. So conduction, as we all know, like it is just a transfer of energy through the solid matter from particle to particles. Like if you take the convection, it's just a transfer of heat of energy to a gas or liquid. Just now we talk about the temperature heat transferring takes place between my body and the ambient temperature or environment. And the radiation is just an electromagnetic waves which directly transport the heat energy through the space. As you can see, even the astronauts also, they wear these heavy, thick space suits just to protect themselves from this harmful radiation. So these are the three modes of heat transfer that normally occurs. Now, how are you going to measure that thing? How are you going to quantify and measure how much amount of heat is being transferred? So we have the basic equation to find out the rate of heat transfer. You can see Q is the heat transfer over a period of time T. K is the thermal conductivity, and A is the area of the area, and the T is the temperature, where T is nothing but like the delta T, you can consider it as, which is the difference in temperature, and is thickness of the barrier. So that's the formula where we can get the rate of heat transfer. Now, British thermal units per hour. What exactly is BTUH? We already discussed about BTU, and the BTUH is nothing but it's just how many BTUs are used per hour. So these two terms are changing. We use them interchangeably throughout the session. And normally when you're talking about the cooling side, when you're making any calculations, when you're coming up with the load calculations, when you are trying to determine how much will be the cooling load, you're not going to mention your units in BTU heads and all that stuff. You'll talk about the in tons. For instance, if you talk about an air conditioner or a chiller, you'll say, okay, I need like 5-ton chiller or 10-ton chiller. You don't say like, oh, I want like 50,000 BTU chiller. You don't say that stuff. So it's just a common terminology. So for the cooling, we'll just stick with the tons and all that stuff. When it comes to the heating, we will talk about BTUH. Well, MBH is nothing but it's 1,000 BTUH is nothing but 1 MBH, and we will talk about the million BTUH also. So down in the line. Again, the most basic things, we have two types of heat, which is sensible heat and latent heat. So the sensible heat is nothing but pretty much the amount of heat energy that you're going to give into a substance to change or rise its temperature from X to Y. For instance, let's take the water. You're going to, for example, the water is at room temperature, maybe at 32 degrees Fahrenheit or like 60 degrees Fahrenheit. You're going to try to raise the temperature to its boiling point, which is either 100 degrees Celsius or 212 degrees Fahrenheit. So the amount of heat required to raise the temperature of that water from its temperature or ambient temperature of that water to its boiling point, not only to the boiling point, I'm just giving you as a reference as a boiling point, but for that instance, any temperature to raise just the temperature of that substance, that amount of heat is nothing but sensible heat. Whereas the latent heat is just the amount of heat energy that you are giving to the body to change its phase. For instance, let's take the water as an example. Just now you raise the temperature to 100 degrees Celsius. So that's the sensible heat. Now for the, if you keep on adding heat to that water, it's going to change its phase to steam. That amount is the latent heat. So that's the difference between sensible and latent heat. Now let's jump into the concepts of building envelope. What exactly is the building envelope, and why exactly do we need to know what is a building envelope? In order to find the heating load or cooling load of a particular property or particular commercial thing, you got to know what is the envelope, which means like where exactly that you want to maintain these temperatures. As you can see over here with the red border, that itself is the conditioned space. What it means is like that's where you are supposed to process your air, whatever the thing that's contained in that particular space. So the building envelope is pretty much, it differentiates between the conditioned space and the outside environment. That's what it is pretty much. So you have to figure out what exactly is the building envelope. As you can see it on my screen, the one with the red border is considered for me as attic is not in conditioned space for now. You can put it, if you want, you can put it, but I'm just saying it over here to show you the difference. What is a conditioned space and what is the unconditioned space? So that's the first step. You have to find out what is the building envelope. That's a few more illustrations to let you know on building envelope concept. So as you can see over here towards the left, the complete building is heated or cooled, whatever that's going to be like, but the building envelope is completely enclosed, the whole building. Whereas towards on the right side, the basement and attic, they are not heated. So the building envelope is reduced, which means less space, which means you have to calculate the cooling loads and heating loads based upon the building envelopes. Now, the other important concepts in the heat transfer, there are like three important things, which is K, thermal conductivity, R is just resistance, and a U value, which we're going to discuss later. So the thermal conductivity is just like its ability of the material to transfer or transmit the heat energy through it. That's what the thermal conductivity is. Our value is just resistance. So it's an inverse of K. So normally you'll measure these things R values. So the higher the R value of a material, then it is a very good thermal resistance. And you can be using that thing as a good insulator in your applications. So for, as you can see over here, for recommendations, typical recommendations for the exterior walls, you prefer to have either R3 to R23 type of materials. And for roofs, you got to have R30 because there will be a lot of exposure to the sun. There will be a lot of heat transfer through that stuff. So you need little more insulating material over there in those portions. And for, if it comes to R38 and R49, you pretty much use in ceilings and attic spaces. That's what it is. So the higher the number R value, it has the better insulation capabilities of that particular material. And U value is just an overall coefficient of heat transfer. It's just a coefficient of heat transfer. So it's inverse of R value. So the lower the U value, it has the greater resistance to the heat flow and it has better insulating capacities. So those three are the very important concepts. Like when we talk about this HVAC stuff also, like depending upon the R values of that particular material, you can use them in applications as needed or as required. Depending upon that particular application, you will choose the right materials. You don't want to overkill it. At the same time, you can design a system where it's going to let all the heat or cool just pass through that stuff. Now, let's jump on to fenestration. What exactly is the fenestration? It's just a fancy architectural term, which simply means openings in the outside of the building. As you can see in the picture, it has a lot of glass curtain walls over here, glass doors and all that stuff. So the fenestration loads include heat losses or gains. It could be both, either losses or gains. It can come through it or from inside the building. It can go away too. The doors, skylights, etc., etc. And they can make a significant portion of the overall load in your calculations while you are calculating, while you are trying to determine the cooling load of that stuff, of the particular space. So they're gonna impact it. It's a significant portion, as you can see over there. It depends upon the architecture of that particular building too, but it's a big portion of it. We'll discuss how you're gonna calculate those fenestration down in the session. The next concept is going to be solar heat gain coefficient. This is something that you have to consider while designing your cooling and heating loads as well. For instance, what exactly is SHGC, which is solar heat gain coefficient? It's just a fraction of incident solar radiation admitted through a window, either both directly transmitted and absorbed and subsequently later released in your. That means like if the sun, right, the glass stuff in the windows, like they will transmit that stuff. And it's just like it's expressed in and as a number between 0 and 1. So the lower the number, it has a very good, it's a very good material, I would say. Then you have to choose windows with a lower SHGC content stuff. The next up is projection factor. As you can see on the picture over here, the projection is just a overhang from the parapet or from the ledge of a building or something, which is just a ratio of the distance the overhang projects from the window to the surface of its height, which is over here, which is just A or B. That's it. That's the projection factor. Even this thing you got to consider that stuff because the shadow will impact this stuff. So you have to consider that stuff also in your calculations and all that stuff. Next concept is going to be refrigeration. So what is refrigeration stuff? So it's pretty simple. Like you already knew about it, but like you are giving electric energy to the refrigerator, and what it does is like it's going to remove the heat from the inside space. That's what it is pretty much doing. So you are giving the work and asking the refrigerator to remove the heat from the conditioned space, which is inside. Air conditioning is the same as refrigeration. Like it's air conditioner, you can consider it as a refrigerator, but instead of cooling the stuff inside the refrigerator, and the air conditioner does is like, it's gonna cool the place, like, I mean, the space, like wherever you put that AC is on. So that's what it is, the difference between, but the concept is the same. So you can use ice as a coolant, but it's like it has the properties of the ice. So it's only like the boiling point is only 100 degrees and the freezing point is only 0 degrees. So you can't use ice as a refrigerant or something. It has its limits. So, but ice can be used as a coolant too. Normally used refrigerants. So there are like multiple refrigerants, but mostly typically R410A is the refrigerant that commonly used these days, which is hydrofluorocarbon, and it has a boiling point of minus 55.3 Fahrenheit. So that's the most important thing. Since the properties of this R410A it has since very low boiling point, so it can be acted as a very good refrigerant, and they've been using these things on all this equipment these days. So now let's talk about the refrigeration cycle. There are four major parts in the refrigerator or refrigeration cycle. One is the compressor, condenser, expansion valve, and evaporator. As you can see on the left side, so the one with the blue line is just referring it to low pressure side, and the one with the red referencing it to high pressure side. So from the evaporator, you have the low pressure gaseous gas state refrigerant is coming out, and it's going into the compressor, and it's being compressed to very high temperature and high pressure gas. It's still in the gas phase, which is going to the condenser, where it's going to remove its heat and condenses back into the liquid. So over there in the condenser, what it does is the gas is being condensed into liquid, at the same time releasing its heat to the atmosphere. And from there, it's going back into the expansion valve. And since the properties, because of the properties of the refrigerant that is being used in the system, what it does is when it expands, it's going to go into very low pressure and very cold liquid. Hence, it is going into the evaporator. Evaporator is the place where you are intending to cool or heat the system. It's going to take or give the heat into that particular system. If you talk about the heat pumps, then it's going to giving the heat into the system. And where if you're talking about the AC or refrigeration thing, it's going to take away heat from that space over there. That's what is going to happen over here. It's heat pumps and air conditioners. Those two are just like quite opposite to each other. Normally, you don't use heat pumps in India, so it's pretty much we don't need heat. But if you're living in a colder country, it's definitely the heating plays a very vital role. Like as me, like I'm over here, and it gets pretty cold, and you definitely got to have heating, and you have to design the systems which are capable of handling both heating and cooling. Like that's what it is. So that's the most important thing about the heat pumps. You can put like one equipment for heating and one equipment for cooling. If that's the case, then there will be your complete space will be filled up with all this equipment. There will be a lot of noise and all that stuff also, which you don't want that. So you got to come up, you have to pick and choose what's the right equipment for the particular application. Again, it's just the schematic of the refrigeration cycle that we just talked about before. So the expansion valves, compressors, evaporators, or condensers is pretty much the same standard layout. Now let's talk about the HVAC systems. Now, there will be like tons of systems. Like these are not only all the systems I'm listing over here, but these are the mostly used systems in the industry. Packaged and split systems, condensers. I mean, condensers, it's not a separate system. You need the condensers for packaged and split systems also. And direct expansion systems, these are the widely used systems these days. And chilled water systems, which you use them for institutional purposes, I would say. Like you don't use chilled water systems for medium range to small residential sectors. You use these things in industrial or institutional things, where you might need a lot of chilled water to take the heat away from the spaces, conditioned spaces. And heat pump systems, which we just spoke, like it's just a reverse of refrigeration systems or air conditioning systems. Next, VRF systems. This is also quite popular these days, which you can control both heating and cooling at the same time from the same condenser, from the same refrigerant. So that's very important, VRF systems. And single zone and multi-zone systems, constant volume and variable air volume systems, and dual duct VAV systems. So these are just VAVs. VAV is nothing but variable air volume. That's it. So we're gonna start discuss about like each system one at a time now. Again, I'm not going to go too deep. I'm just give you an overview of what these systems are going to look like, and that's it. So that's how it's going to be, because it's pretty much this design topic is like it takes like a couple of semesters to finish this stuff. So I'm just cramping up all the information in this 1 hour session. I'm trying to give as much information as possible, so that's why I'm going a fast-paced thing. So let's talk about the packaged systems. What is packaged system? As we discussed those 4 components before, which is condenser, compressor, expansion valve, evaporator, all those things are in one single system. And as you can see in this picture towards the left, so it's all self-contained. Everything is in there. It's all those 4 parts. You'll see pretty much these things in smaller homes and all that stuff. So they'll be called as window air conditioners or through wall air conditioners. That's what the generic terms, but it's their actually packaged terminal air conditioners is the technical word, I would say. Not technical word, that's the scientific word, you can call it. But in general, they call it as window air conditioners or through wall conditioners. So towards the right, you have the split system. As the name says, what is a split system? You have the compressor and condenser in one portion and the evaporator and expansion valve in one. These split systems, you can see them a lot these days too. So there will be condenser on the outside. You run the refrigerant lines, which is a suction line, and the liquid line from the condensers to the evaporators, which is inside those cassettes. You can call them as cassettes. They can be wall mounted or ceiling mounted. You'll see all these things. Pretty much, these things are more popular, but they have their certain limitations also. They have their own limitations. You can't use them like for, if it's like 20 or 30 story building, you can't put these split systems because they're going to take all the space. Like where are you going to put the condensers and all that stuff? So now let's talk about the condenser types. So since the heat is being removed from the conditioned space by the refrigerant, so it's got to be cooled off. So that's where it comes into play. The condensers, that's what it does. So it takes the heat away from the refrigerant. And so they could be either air cooled or water cooled or evaporative condensers also. So it could be anything. So mostly we'll see the air cooled condensers, and water cooled are pretty much we can use water cooled too, but evaporative, until unless it's a big facility, you don't need to put the evaporative condenser. So those are the advantages and all that stuff. So as per the application, you can use these things. There you go. That's one of the most important topics is the chilled water systems. So if it is an institutional, like for instance, take about your university like RVCET, it's a big campus and all that stuff. You got to have certain amount of cooling for that facility, right? So you can't just go and buy window air conditioner. You could buy it. I'm not saying you could not. So you can buy it and you could do whatever you want to do with it, but it's not going to be economical. So it's not going to be energy efficient. What's got to be done is like, if you want to put that stuff, you have to pick a right equipment, as I said. So you got to choose chilled water systems, which means like you will supply the chilled water for all these fan coil units. So what it does is the chilled water, the energy heat exchange will take place using this chilled water. That's what it is pretty much. The concept is so simple. You'll be having refrigerant, and what it does is it just takes the heat away from the system, or it's going to give back heat to the system. If we're talking about the heating mode, that means you need to have required heat for that space. So in that case, heat is being transferred. You don't use chilled water at that time. So there will be different systems. I'm just saying it like that's what it is. The concept is same, the heat exchanging. That's the basic bottom line concept of HVAC stuff too. So on the chilled water system, these are the components you have. You have the chilled water pump, you have the air handling unit or fan coil unit, whatever you call it, and you have the chiller in between, and cooling tower and condenser water pump. So that's the basic components of the two. So here you'll see different types of chilled water systems. You have on the left, you have water cooled chilled water systems. That's what they're going to look like. On the right, you can see air cooled chilled water systems. So pretty much the condenser water is being cooled by water over here, over there it's going to be cooled by air. That's it. So that's the difference. And you have the air over here, as you can see, the limitations of the air cooled systems are you can't have more than 500 tons of cooling capacity of the chiller. So if you need like more than 500 tons, then you've got to choose water cooled. As I said, it all depends upon your application. Like if the cooling loads are more, like for such as your institution or something, then you've got to go with chilled water cooled chilled water systems. And the pros and cons for water cooled and air cooled chillers are over here. For air cooled, you can see the low first cost. The costs are going to be very less on the, not very, very less, but if you compare with water cooled chillers, the air cooled chillers are a little bit cheaper and you have less maintenance, which means like you don't have to maintain that thing and the cost will be lower for the maintenance as well. And for the low ambient air operation also, it's very good for the air cooled. It's very good to use air cooled chilled water systems. As far as the water cooled chillers are concerned, you have their petty, as you can see over here, they can be used up to 3,000 tons also. The capacity are huge and they have very good great efficiencies, and the life is also very good for those things. They last longer. let's talk about air handling units. What is an air handling unit? So air handling unit is just a unit. What it does is it just supplies air to that particular space. And the main components of that stuff, you'll be having an outside air, you'll be having return air, you'll be having supply air, you'll be having exhaust fans, supply fans. You could either have heating coils, you could have cooling coils, as you can see on the picture towards the left. The one red represents over there is a heating coil. And not only over here in the rest of the session, also if you see anything red color, that I'm talking about the heating, but if you see the blue color or towards the right, it's just cooling stuff. So you have the cooling coils and you have the heating coils. You can place them as many as you can. Again, it depends upon the efficiencies and it depends upon the energy consumptions and all that stuff, the requirements. Based upon the requirements, you will pick and choose what you need, and then you will put them in a duct and all that stuff. That's what is, you'll be having thermostats and you'll be having dampers, this and that. We will discuss this thing down the line. But this is the overview of what it's going to look like, the air handling unit. On the right, that's how they're going to look like. This is just a diagrammatic representation. On the right, those are just some typical schematics of air handling units you normally see. So this is a schematic of 4-pipe system. What is a 4-pipe system? As you can see over here for the heating, again, the red things are representing heating stuff and the blue things are representing cooling side. So you'll be having boiler and chiller over there. For boiler, will be used for heating and the chillers are using for the cooling. Again, on the air handling unit, there is a coil over there. You can see the blue lines are going to that particular coil, which is a cooling coil. And the red lines are going to a different coil over there in the same air handling unit. That's for the heating purpose. And outside air, you have the fan blower. What it's doing is it's just supplying the air to that particular zone. You have the fan coil units and all that. Fan coiling units, it's nothing but those are split systems like that. So the ones that cassettes that we were talking about before. Excuse me. And heat pump systems. What is a heat pump system? So it's just a reverse of the refrigerant cycle RS. It's just you are adding that stuff. That's it. So you're adding heat to the conditioned space. That's what it is pretty much. So, as I said, variable refrigerant flow system. These are like most popular these days, where the same system can be used for heating and cooling at the same time. As you can see over there in these particular rooms, they want heat. The people in the in those rooms, they think, oh man, they're feeling chilly. They need some heat. So they're going to ramp up their thermostats, and so the space is getting heated up from the same condenser lines. You can see that stuff. And on the other side, there's some blue representing they want some cool stuff. So it's being done at the same time. That's what it is, VRF stuff. So, and you have constant volume systems and air volume systems. So variable air volume systems, sorry. So constant volume systems are just like they're sending the air, supplying at very constant volume, whereas variable air volume system is like different volumes. For instance, if there is a bigger room, you need to have more CFM of air required for that particular space. But talking about a smaller room, you don't need to put that much air over there in that room. So it's got to be variable air volume, as you can see over there. So maybe it might need only 150 CFM, which is cubic feet per minute. Whereas a bigger room, it might need 300. So it depends. So it depends upon your applications. You can pick and choose that stuff. Now let's come, how are you going to calculate the heating and cooling loads of this stuff? Again, these are some basic objectives you have to keep in mind, like just to piggyback to my earlier conversation, what exactly is our HVAC objectives? Those are the objectives that we talked about before. Excuse me. First and foremost thing for HVAC system is you got to keep in mind the human comfort. That's the first and foremost thing, like it could be heating or cooling. At the same time, it's got to have appropriate humidity level. You can't have too moist or too humid atmosphere. It's going to directly affect your productivity. Like for instance, if you can finish the whole work in 4 hours, if you're in a good comfort zone, and if you're not, the same work could take 8 hours. So where you're losing all the man hours and like the productivity is going into the brain, which you don't want that. So for a perfectly designed system, so you have to consider all these things like the velocity of the air. You don't want the air blown to the face, which is more distracting and all that stuff. It's got to be at a proper velocity, got to be properly ventilated. And indoor air quality. This is the most important thing that's happening right now because of this COVID too, because certain amount of air, which is already processed, is going to be recirculated back into the space. If it is being recirculated, which means there will be a lot of pathogens also. So now with this COVID and all that stuff, people are concerning about it. So there might be any code changes down the line also on that stuff. So what's got to be done to provide better indoor air quality stuff. So that's the most important thing. There's a lot of research going on as we speak. And the noise and vibration stuff, again, if you're sitting in an office or at your institution, like you don't want noisy from the ductwork and all that stuff. It's so annoying. You don't want that. So you got to pick and choose the right materials. How you going to reduce the noise? Like putting sound attenuators or putting duct lining, like acoustic liners inside the duct, where you can, where it suppresses the sound and all that stuff. So that's what, these are the objectives you have to keep in mind while designing your system. So, okay, let's talk about each individually, like each elements, what affects the cooling and heating loads. Indoor design conditions, geographical site conditions, building configuration, outdoor design conditions, building characteristics, internal heat gains, infiltration, ventilation requirements, additional considerations. Each and everything you got to go, you have to come up with some sort, you have to quantify it. So I'm going to discuss that stuff, like how you're going to calculate internal heat gains, how it's going to affect the building orientation on cooling loads and heating loads and all that. So we'll discuss one at a time. Now, as I said before, the comfort zone, each and every person has their own comfort zone. Like some people, they'll be fine with like higher temperatures also, and some people they'll feel chilly. So it all depends upon personal preferences. But ASHRAE, which is American Society of Heating, Refrigeration, and Air Conditioning Engineers, what it says is it specifically defines comfort zone, and you can calculate your heating and cooling loads based upon that standards and stuff. Pretty much whenever you're doing the heating and load calculations, you can put the maximum heating load of 72 degrees. I mean, the temperature would be 72 degrees for heating calculations, or for the cooling calculations, you can figure it out 75 degrees Fahrenheit, which is approximately that. I converted into Celsius also. So as I said before, so most of my presentation is going to be an inch pound system, which is an English system. So just be mindful on the units and all that stuff. Building orientation. So if the orientation of the building is towards the left side, you can see it's very poor because there will be a lot of interaction with the sun and that stuff. There will be a lot of heat gains and losses in that stuff. So the good orientation is going to be tilting the other way as horizontally, you can see towards the right. Space heat gain, space cooling loads. It's again, what exactly is space heat gain? See, space heat gain, sorry, man. The instantaneous rate of which heat enters into and or is generated within a particular space at a given instant of time is nothing but heat gain. While you are calculating cooling loads, you have to remove that instantaneous heat, not instantaneous, that space heat gain, whatever that is being generated in that particular space. So that's what the space and cool loading is about. So you can calculate that stuff with this formula. It's the same formula that we discussed earlier. So that's the formula that you're going to use for that stuff. So these are the things, these are the methods that you're going to come up with that we're going to use to calculate the cooling loads and all that stuff. So I'm not going to go on each and everything, but pretty much we're going to stick with this thing, that CLTD method. That's the pretty much we're going to use in our calculating loads, cooling loads, all that stuff. So what exactly is CLTD, cooling load temperature difference? So it's a very simplified method. And that's what we're going to use in doing our calculations and stuff. So in the CLTD method, so these are the external loads and those are the internal loads. External loads are like roof, exterior walls, etc., etc. And internal loads are even from the people. If there are like 1,000 people in a room, then people is going to add up all that some sort of heat into the system. So that's the heat gain. So you have to remove that heat. So while calculating your cooling load, you have to consider all these things. You have to come up with like the quantifying, how much would be the load, how much would be the people's internal load, how much would be the lighting load, how much would be the equipment load, how much would be the motor load. So once you compile all these things, then you're going to add up. At that time, you can figure out, okay, this is the cooling load I need it in order to maintain certain amount of temperature in that particular space. Once you have your load determined, then you'll go and choose appropriate HVAC system that's required for that particular application. Again, as time is very limited, I'm not going to go deep into all that stuff. So let's jump onto these things real quick. So roof loads. So that's how you're going to calculate it. So the roof loading is like USCLTD. It's pretty much the same equation. It's a basic conduction equation, just changing the delta T with CLTD value. That's it pretty much. you'll get the U values of the particular material that is being used in the calculations from the ASHRAE tables. The ASHRAE, it pretty much is, it has like 4 volumes, not volumes, it's like the 4 books you have it. So they pretty much have everything that you needed in calculating for all this stuff. So again, exterior walls, windows, and all that stuff, even they have the loads too. So that's how you're going to calculate the exterior wall loads. And you have the partitions, same equation, you're just changing the materials and all that stuff. And the people, as I said before, the heat and moisture are given off by the human in different states of activity. For instance, now I'm sitting over here and giving you a lecture. So my activity levels are more. So I'm gonna generate more heat, as opposed to people who are listening on the other side. Their activity levels might be a little bit less than mine, so they might not giving that much amount of heat into the system. So if there are like 50 people sitting with me over here, that load is going to be considerable amount. So you have to figure out how much amount of heat being given into that space while calculating the cooling loads for that system. So those are the formulas where SHG and CLFs are just, you can get those things. SHG is sensible heat gain, and again, latent heat gain. You can get that stuff from the ASHRAE tables too. I'm going to show you how those things are going to look like in the next slide. So that's how they are. So they are giving that stuff like what is the activity level and where those people are sitting in, and how much would be the SHGs and all that stuff. Over here, see, I'm not quite sure whether you can be able to see this thing clearly or not. So this is from the ASHRAE handbook. So there are like 4 different books over there from the ASHRAE. So you can get all this information, and that's the table, and you can get all this information. Like if you're sitting in the office, or if you're sitting in a theater, if you're sitting in a factory, or if you're in a dinner hall, if you're doing something, if you're doing bowling in a bowling alley. So these are the amount of sensible and latent heat gains that you're releasing to the system. So we'll pick these numbers, we'll multiply with the number of people in that stuff. That's how you're going to calculate how much load is being given to the system by the people. That's how you're going to determine the people load. Again, the lights, you'll be having tons and tons of lights if it's a skyscraper and all that stuff, right? So they'll be having certain amount of wattage. So you have to calculate, so which means like it's giving some heat. If you multiply, if it is like 1 watt or 2 watt, that's okay. But like you just multiply, each and every light bulb has 2 watts, and just multiply with who knows how many. So maybe like 1,000 light bulbs. If you multiply that thing, it's going to be significant. So you have to figure out that stuff also. Again, ASHRAE comes into play. They have their standards. You have to come up with the load and all that stuff using formulas as shown over here. Equipments, man, you'll be having computers, printers, whatnot. All these things are heat generated. They give some amount of heat into the space, which is going to be heat, instantaneous heat gain over there. You've got to figure out that heat while doing your cooling load calculations. That's how you can come up with all this stuff. So those are the formulas, you can get it. So pretty much the information, whatever that you need it for that particular thing, is that you can get it from the manufacturer's plate on that particular equipment, or from the ASHRAE as well. Infiltration, it's again, is just an uncontrolled passage of outer air into the building through unintended leaks in the building envelope. You can calculate the loads using that stuff. CFM is nothing but the airflow into that system, cubic feet per minute, and you can get that load, sensible and heating loads. Sensible load and the latent load of infiltration. Man, what's going on with me? Maybe I don't have enough coffee today. It's on ventilation loads. As I said, you'll be having air handling units, you'll be having rooftop units, you'll be having tons of equipment. They are putting that stuff too into that space. So while calculating cooling loads, you got to figure out how much it's going to be. So you have, again, the formulas over there. So whatever the CFM is going to be, you'll calculate it, and then you'll come up with particular quantity, how much would be this ventilation load. And that's how you're going to do it. Motors and all that stuff, it's similar. I'm not going to go too deep on that stuff. Let's talk about the ductwork design. What is ductwork? It's now you have the air handling unit. How are you going to supply the air from that air handling unit into the space where it's needed to be? You're going to connect it with ducts. And that's the duct design. And it's got to be properly designed. It's got to be 2 huge big ducts. You can't put them over there. It's going to be, first impact is going to be, it's going to take a lot of space. Second, it's very costly too. So keep in mind, while designing a duct system, what's got to be done is you have to minimize the pressure drop throughout the system of the ductwork, keeping the size of the ductwork to be minimum. So these are the duct design criteria. You have the space, you have to consider space, installation costs, air frictions, noise levels, duct heat transfers, course, blah, 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 whatnot. On the right, you can see the schematic diagram of air handling unit 2. You have the, over here, you have the supply air trunk, which is the main branch. You'll get it from there. And the branches will be taken off from the supply. You'll be having the final terminals over here, which are called as diffusers. Towards the left of the schematic, you can see the return grills. Means like some of the air that's being supplied into the space is being recirculated back into the system. And certain amount of outside air is also being taken into the system. For instance, now you're putting so much of heat or so much of cooling into this processed air, right? You can't just exhaust all this stuff because you already spent so much of money over there. You can't just exhaust all those things. That's what this recirculation is all about. So a portion of it is being exhausted, but mostly it's being recirculated. To compensate that exhausting portion, you got to take some outside air. So you have the pressure components, you have to figure out this, how much would be the pressure losses and all that stuff. Whenever there is a flow, there will be loss in, the total pressure of the system, which means like you're going to lose pressure with the friction losses and all that stuff. You have two components of the total pressure, which is static pressure and velocity pressure. It's like similar to potential energy and kinetic energy. It's the same concept. So the static is considered as potential thing, and velocity is based upon the kinetic energy form of the stuff. So the total pressure throughout the system is going to be, you're going to lose the total pressure for any system. Like for instance, if you take on this diagram over here, this is the ductwork. The top line over here is representing the total pressure of the system, where over here you're putting a fan, which means that you're manually putting a pressure. That's why the pressure rises over here. Otherwise, it's going to go like this. The total pressure is always going to go down with the friction losses and all that stuff. Whereas the static and velocity pressures, they'll change. Whether they can go up or down, it depends upon the orientation and depends upon the cross section of the duct, depends upon the equipments and all that stuff. So that's what it is. The total pressure is always going to go down unless you put the fans and all that stuff in the ductwork. But the static and velocity pressures, they can just go up and down. It depends on the system, like the shape and all that stuff also of the fitting. You have multiple duct based upon the pressures that's being handled in the duct. You have the different types of the pressure duct systems. You have, if it is less than 2 inches of water column, then they're considered as low pressure ducts. In between 2 to 3, they're medium pressures, and anything more than 3 inches of water column of static pressure is considered as high pressure ducts. You'll be having friction losses, dynamic losses. Again, that's air. The ductworks are being used to supply the air. Air is a fluid and has viscosity, turbulence, and all that stuff, whatnot. And the friction losses, you'll be having friction losses, and the dynamic losses are from the fittings. The friction losses is just from the straight lengths of the ducts also. You would calculate all the losses with these formulas. You need these things while you determine what size unit you need it and how you're going to design the duct and all that stuff. I'm going to show you an example. I'm going to skip these things and let's concentrate on this thing. It's taking too long. So let's talk about boiler plant. What is a boiler? Boiler is just, it's just a component. So what it does is like, it's a heat exchanger where it takes the water and it converts the water into steam. It can't do it by itself. So you have to supply the power, like how the power is being supplied to the boiler, which means you have to put a burner over there. So what burner does is it burns. That's what it is. Like it burns, it takes the fuel, well, it could be a natural gas or number 4 oil or number 2 oil or number 6 oil, whatever the thing is. So it's going to convert, it's going to burn that fuel and gives the heat energy to the water, and thereby it's converting this both sensible and latent heat and converting the water into steam. That's what it is. And those are the typical components that are involved in a boiler plant. I'm talking about this thing for commercial heating application. I'm not talking about anything else. I'm just concentrating on this stuff, as this is something new that we normally don't deal with this kind of stuff back home. So that's what I'm concentrating. It's something new. Rest of the air conditioning or air handling and all that stuff, pretty much you guys already knew about it too. This is something new, so let's concentrate on this one. So those are typical components. You'll be having boiler feed tank, and I will tell you what the purpose of each and everything is. So vacuum and condensate receiver tank, chemical feed tanks, louvers, dampers, fuel oil tank, and air handling units, draft inducers, air compressors, and like blow-down separators. Man, That's a whole big list, right? Let's talk about this thing. So the first and foremost thing, combustion. Combustion, you need to have combustion air for the effective combustion process to takes place, right? So these mechanical equipment rooms are huge, and these boilers, they are so big too, and you can't just uh, take this water of the air that's in there. So I'm going to show you some pictures. They're big. It's not that much. I mean to say, like, it's not small. I'm talking about huge facilities, like, as you can see. Uh, Come on. Are you seeing my screen? Do you all see my screen?
Yes, 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 sir, yes, sir.
Not the presentation. I'm showing some pictures. I'm not quite sure whether.
So it is not visible, sir.
Okay, sorry. Let me look at.
So you have to share that particular image. You have shared only the presentation mode.
Gotcha. Hang on one second. Let me switch.
Again, go back to share.
I will. 1 second. Sorry. What the hell just happened? Now, can you all see my screen now?
No, 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 sir.
No, not yet.
No, not yet.
Sorry.
First, we have to stop the first screen, sir. Whatever you're showing, boiler combustion is there, no?
How about now?
Yeah,
now
okay,
it's
okay. Now it's
My bad. You know what? Just all right. So these are huge. So I don't want to go into
It is not visible. Just Shivaram sir, again give the host right.
share screen. Okay.
Now you can share
now you can
the.
share, sir.
What now?
Yes, yes. Now it's
Yes,
okay. Now it's okay.
So these are huge boilers. These are, I'm not talking about very small little ones. So they'll be having huge facilities in the mechanical room. So you have to size the combustion air and all that stuff also properly. So that's what I mean to say. So, and okay, now you can see my presentation stuff, right? Are you still seeing the picture?
Yes, sir.
Still seeing the picture.
I messed it up, man.
Again escape. Again go back to share.
Got it. How about
Yeah.
now?
Yeah.
Right?
Now we can.
There you go. So the first and foremost thing is, like, you have to size. You have to bring enough amount of air required for doing the proper combustion, right? First and foremost thing is called louver. What exactly is the louver? It is just this is how it's look like. The louvers are just like, these are just aesthetic components which are installed on the facade. Facade is nothing but face of the building, just to allow air or light to pass through. They have either angle flats or like flat strips. As you can see over here, these are angle slats. So the purpose of these things are just to allow the air into that particular space. That's what it is pretty much. Now, you need to have air for doing the combustion. How big these things are sized to be. You can make the openings like big, like 20 by 20. Who knows? You don't want an opening of size 20 by 20. So there are some restrictions on the stuff. The codes will say how much air is required to provide to that particular thing. As per International Mechanical Code, MC 703 states that you have to provide a minimum of 1 square inch of space for every 3000 BTU H input of the boiler system. Before we come up with the loads, right? How are you going to calculate all that stuff? And once you calculate all those things, like, you're going to size the equipment that's needed for that size, then you have to come up with louver dimensions. The louver dimensions are based upon this thing. So that's how you're going to come up with this size of the louver. Sizing of the louver is also most important thing when it comes to combustion air. So now you have the louver. At the same time, you can't have huge louvers, right? So sometimes you won't be having enough space over there. What if the calculations call you that you have to put like 20 feet wide by 20 feet high louver? That's not feasible. You can't put that big size louvers over there. At that time, what you normally will do is you have mechanically supply the air, which means like you'll put a small fan over there. And So now, once you're putting the fan, you got to come up with, okay, how big size of fan that you have put it over there. Again, the code will calls for 0.35 CFM per 1000 BTUs are required. So it depends upon the load that you need it. You'll calculate as per the load, and for every 1000 BTUs, you got to provide 0.35 cubic feet of air per minute of air, which is 0.35 CFM of air. That's how you're going to design the louvers and stuff. Now you have the opening over there. Now it's the air is going freely in and out over there, so which you don't want that too. So you have to block it because it's already processed place, right? So you are already processing air inside the building. You don't want all that stuff to go out, but there is an opening over here with the louvers, which you don't. So what you're going to do is there is one more thing called damper. So this is just a section of the louver. This is how it's going to be looking like. As you can see over here, angle slats. So the air will just go through. This is inside and outside. They'll just go through like that. So now this is how the louver is going to look like. Now I'm talking about the damper. What exactly damper? It's just, you'll put these dampers. They look similar to the louvers. You'll put those things behind the louver over here. What it does is it will control the flow of air, which means whenever you need the air, they're going to open up. Whenever you don't need it, they're going to close up. That's how you can prevent the air to just pass through the louvers. Louvers are meant for just openings and all that stuff, but dampers are nothing but for controlling the flow of air. Now you have the dampers, which close and open. You can't have a man stand by over there, right? Whenever you need it, they can't open, they can open it or they can close it. You don't want the man just stand by over there for doing that stuff. So what you normally do is you'll put a motor over here. The motor, what it does is like it just opens that stuff up whenever you need it. So the boiler will send a signal whenever it wants to turn on. It's going to send a signal from the relay to this stuff to the motor on this damper. What it does is like it's going to let this damper open up as boiler is calling for heat. So you better open the damper up. So that's what it does. Now this will, you have the shafts and all that stuff. They'll open up the damper and the air will flow through from outside and that stuff. There's one more concept over here, which is called a whisker switch. It's called a whisker switch. Whisker switch is this. This is how it's going to look like. So this is the damper, and that's a damper damper motor, sorry. And you can see they can open and close like this with this motor and the stuff. Now, boiler is telling this motor to open up the damper. Now the boiler doesn't know whether this thing is open or not. How do you figure it out whether that's open or not? Like if there is not enough air for the combustion to take place, there will be a lot of energy wasted. And CO will be built up over there and it's going to be deadly. Once the CO builds up, it's a deadly gas and it's can become deadly to the personnel over there, to the maintenance personnel, all that stuff. So this small little device is called a whisker switch, or generally they call it as a rat tail switch. You can see it's in shape of the rat tail. So what you do is like you just put it over here. The moment these flaps will open up, this is so flexible, it's gonna tilt that stuff up, making it the contact. And this thing, the whisker switch is going to send back a signal to boiler again stating that, okay, now listen, you asked for motor to open up and the damper is open now. So you're good to go, you can fire it up. So that's the control sequence of this thing. You have to make sure the air is coming over there for the proper combustion to take place. Now we have the proper amount of air over there. The next step would be flue gases. Once the combustion is happened, so that's how the boiler is look like. This is just a Scotch marine boiler. This sort of boilers you could see back in olden days, and steam locomotives also. That's how they look like. They're kind of longitudinally long and all that stuff. So as you can see on the right over here, the flames are going over here, heating up the water. This is a fire tube. Fire tube means you won't be having water in the tubes. There will be like multiple tubes over here, like just to pass through for effective heat transfer to take place. The fire or heat will transfer through these pipes, and there will be water surrounding these tubes, and that gets heated up. And when it gets heated up, it's going to go and generate the steam. That's how it's going to work, right? That's the basic concept. It's just the heat exchange principle. So there are multiple types of boilers. Again, low pressure boilers, high pressure boilers. You have firebox boilers, Scotch marine boiler. This is a Scotch marine boiler, and they'll be having again, it depends upon the characteristics and depends upon whether you have space available over there in your mechanical equipment room. That's how you're going to come up with this selection. That's just the dimensions and all that stuff. I'm just giving an overview of this stuff. I picked up only one example. There will be like tons and tons of manufacturers, tons and tons of model numbers and all that stuff. I'm just giving an example of this thing. As I said, this takes, I would say, at least 2 semesters. I'm just cramping up all that information, try to give the information in this 1 hour or 1.5 hour session. I'm trying my best. And I'm going super fast mode also. I'm not sure whether you guys are following up or not, but I can't do anything else. So I'm going to give you my contact information down the session. So if you guys have any information, or if you're interested in getting to know more about this, then maybe we can talk about that stuff. It's up to you. So, but just to give you a brief overview of what's going on over here. So this is how a burner is going to look like. So it's just it's a Webster burner, and it has it's just a picture of that stuff. And the boiler feed. Boiler feed is like, you need to have what? Oh, we're talking about the flue gases before, right? So my bad. Let's talk about the flue. So now the combustion area is, once the combustion process is done, then you'll be having flue gases over there. That's got to be exhausted out, right? So you have to design the system so that you can dump all that stuff outside. You don't want that stuff to stay in the boiler room. So let's go to draft calculations again. The moment you start with anything, then there will be a design for that particular thing too. So I'm going to show you a picture of the breaching and the flue gases exhaust and all that stuff. And can you see this thing? Are you guys seeing my screen? I think so, right?
Yes, sir. It's coming.
It's a PDF, not the presentation.
Yes, PDF.
Okay, got it. So there you go. I'm showing a boiler room layout over here. You have like 2 boilers over here. And as you can see, the exhaust ductwork also. This is an exhaust. This is an exhaust. So once that stuff, the combustion process, then you'll be left with these exhaust gases. So you have to remove all that stuff from here to outside. So this is the chimney over here. It's a liner, you can call it as. So from this point to the boiler outlet, this is called breaching. So, and from here, this is called a chimney or chimney liner. The natural process that's happening over here is called draft. What the draft means, like, whenever the air gets heated up, right, the density of the air becomes low, and cold air has more density. So the cold air in this room is going to push the hot air that is being generated in the flue gases outside. So that natural phenomenon is called draft. That's why you see these chimneys, right? So even if you go to an industry or something, these chimneys are huge and long. So the only purpose is like just to create enough draft so that they can just exhaust it out properly. So now designing of these systems is a task too. So you have to properly design these venting systems. How are you going to design it? So first thing is, again, this chimney on this particular example I'm showing, this is the project that we are currently dealing with. So this is the chimney height is probably like 80 feet over here. So now the chimney is of 80 feet high. So you are putting a chimney to exhaust these flue gases from this boiler out to the atmosphere. So you have to calculate the available draft from this chimney height. So what you got to do is calculations. Okay, let's jump on these calculations. You have to calculate the available draft that's coming from that height of the chimney. So these are just the terms. D suffix A is just the available draft that you're gonna get it from the height of the chimney. These are just like what are the terms that I'll be using in these calculations. I'm just explaining that stuff. You have the density of air at so-and-so temperature and pressure. Rho C is the density of the flue gases and the temperature, ambient temperatures and exhaust flue temperatures. You have the flue gas flow rates and all that stuff. So now you calculate how much draft is available. How are you going to calculate the draft? So again, as you knew all the thing, that's almost like 70. Why I put 70 feet over here is, as you can see, the boiler outlet, it's already 10 feet away. Is 10 feet above from this thing, from base. The 80 feet of this chimney is from base of the floor, but 70 feet is from the outlet over here to this one. So you have to figure it out only from the outlet. So that 70 feet is the height, pretty much the usable height of the chimney, I would say. And then you have the 70 feet height of the chimney, and you are figuring out like 32 inches of round duct over there. So you're going to calculate how much the flue gases are coming out from that chimney of burning that much amount of fuel. So these GPHs and all that stuff itself, fuel flow rates, you can get it from the burner manufacturer's catalog, like how much fuel is being burned in an hour using that burner. So if you put all that information, you'll calculate how much amount of flue gases are coming out from that particular mechanical equipment room. In this case, those two boilers are giving 5,690 cubic feet per minute of flue gases. So you determine this much amount of CFM. Now, what would be the weight of that stuff? So you'll calculate the weight of the flue gases also. You have the formulas and all that stuff. So I'm figured out over here, it's a 25% excess air just for combustion and all that stuff, excess air. So for instance, if you need 100% air for combustion, I'm even putting 25% excess air, like just for even effective combustion and all that stuff. So we don't care about like excessive combustion and all that stuff, look, just for excess air over there. So with all this information, once you put it, so I'm having a 0.2853 inches water column of draft available with that chimney. So with the 70 feet high chimney, I'm already having 0.28 inches of draft, which means like, this is the positive draft. Now, you have over here this breaching on chimney, right? So there will be friction losses of all that stuff. Now you have to calculate the friction losses of the flue gases that flew through all these things. You have the fittings over here, you have the straight length of duct and all that stuff. This is how you're going to calculate. So you come up with, so the straight length, the size of the duct and the length of the duct. And why I'm putting 2845 CFM is like I'm taking this farther out boiler over here, this boiler, because the farther it gets, if this one has enough draft, obviously the closer one has enough draft over there. You don't have to calculate this thing. You always go with the farther out one. So you can calculate the draft from this boiler and all that stuff. So if the total CFM I'm coming out from this one is 54 something, so from this boiler, it's half of it. So it's like, that's why I'm figuring it out over here, 2845 CFM from one boiler. And see this details 0.33 from the ASHRAE stuff. You have these friction losses per every 100 feet of duct work from the tables below. Okay, from the ASHRAE tables, I would say so. See, this is old, some 1970s version of ASHRAE book and all that stuff. You see this thing? You'll be having sizes of duct over here, 24, 22, 20 inches. These are just circular ducts and stuff, okay? And as you go over here, you see the friction losses for every 100 feet of that particular sized pipe. So now you have 2800 CFM. On this page, you have only up to 2000, but we have 28 something, right? So, or 24 something. So now you go over here for that particular sized duct, and with the CFM over here, you'll come up with this friction loss for every 100 feet of that one. So I come up with 0.33 over here in my calc. So that's how you have to come up with this number. So once you have that one, you have some correction factors for the temperature. I'm not going to go detail into that stuff. That's how you're going to calculate the friction losses for the straight run pipes. So that's about the straight runs, right? So now you have the fittings also over here. You see this, you have 45 degrees elbows, you have 90-degree elbows over here, you have these Ys, plenty of fittings. So every fitting, even the sizes changes, you'll be having a pressure drop over there. Sometimes even you can gain pressures also, depending upon the fittings. I'm going to show you an example where you're going to gain the pressure over here. So let's talk about the bend. Bends means like these are just the fittings I'm talking about. So you have 90-degree elbows over there, you have 30-degree ones and all that stuff. Again, you'll calculate all these coefficients like what we did before, and you'll incorporate all the values in this stuff, and you'll get this. You'll determine the friction losses and all the fittings also. That's what I mean to say. So now you have the transitions. Transitions are nothing but area changes. Over here, as you can see, there is an area change from the 20 inches round fitting is being changed into 30 inches round. So there is an area change apart from just a fitting over there. So you have to figure out that thing also while coming up with your calculations and all that stuff. So that's what these are, the transition. These are type of bends, ED41, ED. I'll show you what exactly those things are just in a minute, okay? And converging T's. Converging is like over here, as you can see, this is a converging T. This is a converging T. So that's a fitting over there. So there's a fitting, and you have to figure out the transition also, area changes in this particular area. That's how you'll determine these things. Over here, as you can see, you are gaining. I put it in red over here. You're just gaining, or it's not a pressure drop actually. You are gaining something over here. It's not a loss. So that's why I put it as a negative over here. As we're talking about the losses, with the negative, it comes as a positive. So that's what it is. And you will come up with all these things. You will consolidate all the losses, the pressure losses. As you said, the available draft we have is with just this chimney, we have 0.2853 inches of water column. Our pressure we already have is the draft. So we put all that stuff like total friction losses due to straight length ducts. That's the amount of friction losses you are getting it from the straight lengths. That's the total amount of losses you are getting from the fittings like bends. This is from the transitions. This is from the converging plates. Once you add all that stuff, you'll have this 0.1916 inches of water column. The stack effect, which is from the height of the chimney itself, we have a positive of 0.2853, which means like, and I'm going to just take like as a good rule in the design, right? You have to come up with some sort of factor of safety just in case. So I put like 10% extra. So with the losses of 0.19 inches of water column, with 10% factor of safety, I get it around like 0.2 and something like that. So once you put positives and once you take the difference, you have 0.075 inches of water column of positive draft available at the exit of the stack, which means like we have enough draft, which also means that whatever the exhaust gases that are being built up in the boiler can be able to freely exhaust to the atmosphere. You have to make sure whatever the system that you are designing is going to be working. So first we talked about the combustion air. Now you talk about the exhaust gases freely dumping that stuff outside. So you have to make sure you have enough draft. So we do have in this case, we do have enough draft. So we don't need any draft inducer fans. For instance, if you don't have enough draft, which means like if the losses are more than the gases, whatever that's being generated in the boiler, they're not going to go outside. They're going to stay there. At that time, you can't build like, for instance, right? You can't build a chimney like 200 feet high. It's going to stick like crazy. Like how are you going to build that stuff? What is the point? So the easiest thing is how you going to resolve that sort of issues is just put a fan, exhaust fan. It's called induced draft fan or draft inducer. It induces draft. So what you're going to do at that time is, if, for instance, not in this case, if you don't have enough draft available with this chimney, you'll put a draft inducer fan over here. What it does is it's going to suck all this stuff out and throw that stuff outside. Pretty much that's it. It's that simple. But you have to make sure whatever the system that you are designing is doing what it is supposed to do. That's what about the flue system. So we talked about the combustion, we talked about the exhaust, right? So now let's talk about something else. What is boiler feed? Boiler feed is, as the name says, like it supplies the water to the boiler. The boiler is keep on converting water to steam. That will be less, I mean, the quantity of water is coming less and less. So it's got to be dumped with the water again. That's the purpose of this boiler feed. Again, you have to design the sizing. At the moment I said you're putting in equipment, you have to size it properly. This is how you're going to size the boiler feed tank. How big the tank is going to be. You can't have like huge tank over there, right? If it is not necessary, if it is not required, why do you have to put that much size tank? So for every design, it's got to be appropriate. Like you have to figure out what would be the size of the tank. So that's how you're going to calculate. Once you calculate the loads and all that stuff, you'll come up with BTUs. You convert that BTUs into BHPs, which is boiler horsepowers. Once you know the boiler horsepowers, you will use this formula to get the, I mean, like for instance, example I gave you over here, for a 500 horsepower boiler, you got to have 345 gallon tank, boiler feed tank over there. It's not an oil tank, it's just the water. It's going to supply the water. So it's going to have a reserve of 345 gallons in it. 1 gallon is pretty much 3.8 liters of water. You can do the math and you can come up with what are the number that it's, excuse me. So now we have the 345 gallons over here. Again, I put the factor of safety of 1.5, my bad. 1.5 over here, that comes to 517.5 gallons. And I choose a tank of, because even if it comes to 517, right, there won't be a tank like, there'll be like even size of tank. They'll be having 300, 350, 375, 450 like that. So they don't have like 517 or 550. Either you can go with 550 gallon or you could go with 500. So it's up to you, so, or 525 gallon. So you can pick and choose. That's what I mean to say. That's what I'm trying to say over here. So that's how you're going to size up the boiler feed tanks and stuff. And that's pretty much the schematic of the piping of boiler feed tank. So pretty much it's going to supply it, and you have this city water coming out from the municipal water coming out into the system. You'll be having this reduced pressure zone assemblies, which is an RPZ. That is also the most important thing, but that will be designed by the plumbing engineers. We don't have to worry too much about it. The main purpose, its purpose is as a check valve. What it does is it doesn't let the water to go backwards. That's what it is pretty much. And it reduces the pressure also, because the city mains would be like 80 PSI, pounds per square inch of water. They'll be having, you don't need that much pressure going into the system. It's going to ruin all your equipment. So you're going to have like pressure reducing zones and all that stuff. That's what it is. But that's the plumbing engineers thing. So we don't have to worry too much about that stuff. So that's the boiler feed pump and stuff. Being HVAC designer and stuff, that's what I mean. Not like as a in a different sense or something. It's as being, as we are talking about HVAC design stuff. So this is another typical layout. As you can see over here, the boiler feed discharge is going into the boiler. So this is just the schematics. I'm just giving an overview. I could go and talk about this thing for hours and hours, but now it's not the time for that stuff. So just giving an overview of the schematics. Now the other concept is vacuum and condensate pump. What is a vacuum and condensate pump? Why do you need it? So now you're generating steam, and the steam is being distributed to where it's going over there, right? And certain amount of stuff gets condensed when it exchanges its heat in the room. And that once its steam condenses, it's going to become into water. So you got to have that water back to the system. So these pumps, what it does is it's going to suck with that vacuum over there. It's going to suck that condensate back into this one. And that's what it is. Once the vacuum sucks that stuff, it comes over here. The bottom one is called the condensate receiver, and the top one is the vacuum. You can see 2 pumps on the vacuum and 2 on the condensate return 2. Once it gets over here, the condensate, from the condensate tank, this thing is going to pump back into the boiler feed. Over here, you see it. This is the, see over here, it says like it's coming from VCP 1 and 2. VCP is vacuum and condensate pump. You have the condensate coming back into this boiler feed tank. Whatever the amount that you're losing it, to compensate that stuff, you're filling it with the fresh water. That's the scenario over here. That's what's happening. Not everything is going to waste, but at the same time, whatever that you are going to the waste is coming back to the system from the water, from the outside water. That's what it is. No, you can't just dump the water straight away into the boiler. You can't do that. Like if you do it, what's going to happen is like it's the water has like it's many components. Who knows what's in there, like calcium, nitrates, this and that. So you got to remove all the stuff. It's gonna corrode the stuff. The boiler material. Boilers are pretty much made of steel. They get corroded too. So you have to treat the water that's being dumped into the system. Where the thing is, there is one more concept called chemical feed. So what this thing will do is it will dump the nitrite into the boiler feed system, and to maintain the pH of the water 8.5 to 9.5. If the level, I mean, they'll take the measurements and check, like if the level falls under 1000 ppm, then they'll dump some more chemical into the water. That's what it will protect the boiler. That's it. So just to give them more life for the boilers and stuff. So you have to treat the water that's going to the boiler. And we spoke about these things: boiler breaching, which is chimney, draft user fans, which is just pretty much about the exhaust and the flue systems and the draft calculations that we just spoke about. That's what these things are pretty much about. And there's this called condensing boilers. They have the only the positive thing on this, not a positive thing, the advantage of these condensing boilers are like they have very good thermal efficiencies. But what they do is like they take the latent heat of evaporation of the water vapor in the exhaust and turning back into the heat. I mean, it's going to take the heat from the water vapor in the exhaust gases. So that's how you can get the more thermal efficiency of the boilers. These are the condensing boilers, but you can't use these condensing boilers in bigger plants. So it's only for smallest types. Sorry. And this is another schematic of fuel oil tank. As I said before, you'll be having like multiple, you can pick and choose the fuel you want to burn the water over there. So it could be either natural gas, it could be either oil and all that stuff. And again, you have different grades of oil. Number 6, which is a heavy oil. And now I think there are some environmental regulations that you can't use number 6 oil because it's like, it's so dirty and like you'll be having a lot of pollutants, which you don't want, especially in New York City, they are abolishing that stuff. So what are the facilities that they are already having, they've been converting into natural gas or some lighter oils, which is number 2 oil, that's most popular too. But mostly it's, before they were using coal just to burn that stuff. That's way back. I wasn't even born yet. So it's that's how it was. And now it's pretty much everyone is using natural gas for fuel burning and stuff. So you'll be having fuel tanks over here and like fill lines. You have the fuel oil pump. What it does is supplies oil to the boilers and all that stuff. And you'll have the return pipe, which is fuel oil return. So all that, whatever the unused oil over here will be like, it's going back to the system. That's what it is. That's the schematic of the oil. And this is a schematic of the gas piping. You'll be having the gas, so natural gas from the street. You'll be having safety valves over here. Yes, for instance, like if there's a gas leak, right, you are installing a gas over there. If there is a gas leak, so what's going to happen? It's going to be deadly. So you'll be having gas leak detection systems. What it does is you'll put these sensors over here. They're going to detect if there is any levels of rising in natural methane or ethane over here. So what it does is like, it's going to shut off the supply to these boilers. So these are safety valves over here. As you can see over here, 6-inch safety shut off valve, which is also called Mag-Zahn valve. So that's the purpose of this Mag-Zahn valve. It's just a schematic I'm just showing you, that's it. It's nothing important. And like it's the schematic of hot water heater and ventilation. Again, now you're supplying air, right? Let's talk about the ventilation for a bit. And then you're supplying air to a particular facility. Now you are taking some outside air also. You can just throw whatever the air that you already supplied outside, right? Some of the gets recirculated and some portions got to be from the outside air. So these sections, I mean like this mechanical code 403 states like how much air that is required for hour. It's called air changes per hour. How much air is required? How much fresh air is required? So those are the formulas. You can get all this information from the tables and stuff. Like it depends upon the class of the application, right? For instance, if it is a classroom, you got to do like certain air changes for every 6 hours, and it's got to be 300 CFM got to be provided. So that's how it's got to be done. So there'll be that standards you'll pick and choose depending upon where your design is going to be. So these are the formulas you will calculate and you'll come up with CFMs of that stuff. That's how this thing's got to be done. And as just said over here, it says that, for instance, over here, right? So let's talk about institutional. This is just from the mechanical code I'm referencing it to. Let's take office. If it's a conference rooms, right? So, and they're talking about like, excuse me, you got to put like 5 CFM over here, 5 CFM for every 1 square feet of area. So if it is 100 square feet area over there for the conference room, then you have to provide 6 CFM. And since it's for every square feet, you got to put 0.06 CFM. For 100 square feet, it's got to be like 6 CFM. That's how you got to calculate. You'll put these numbers, and depending upon the occupant capacity of that particular space, you'll come up with how much air is required. And insulation, this is also one of the most important concepts, which is falls under energy code compliance. Energy code is like, now you're providing all that steam and all that stuff. Now that's got to be distributed, right? So you will be having these piping systems, steam supply, condensate return, all that stuff is hot stuff. The pipe is going to be too hot. So if the pipe is hot, the ambient air surrounding that pipe is going to be at room temperature. So there will be a lot of heat loss, like the heat transfer is going to take place over there. What you got to do is you have to minimize that stuff. How are you going to minimize it? You're going to put the insulation. So how thick that insulation will be depending upon these codes over here. So it's got to be per this thing. For instance, like let's talk about the steam. So if it is normally the steam that we in the low pressure boilers and all that stuff, it's going to be of the temperature will be 251 to 350 degrees. Over here in this range. So the insulation thickness got to be this size. So that's what it is. So you have to pick and choose the insulation for your system so that you can reduce the losses of heat wastely going out. So that's what it is pretty much. But you have to design everything as per the codes, whatever that complies to. Now you have the steam. Now what you're going to do with that steam? You have to send that steam to wherever it's needed. So you'll be having multiple systems, but mostly we'll deal with pneumatic control system. Pneumatic is like we'll use the air compressor over there, and DDC system. This is quite new, where you can control it from the internet and all that stuff also. You can just sitting in front of your computer, you can set the temperature of the particular room and all that stuff, and you can do it by automated and all that stuff. Even with your phone also you can do it. So pretty much all the older systems are being converted into DDC systems, which are having backnet capabilities also. And what are the components in climate control? You'll be having radiators, convectors, fin tubes, unit ventilators, man, whatnot. So all this stuff will be there. Let's talk about real quick of these things, okay? What are convectors and radiators? I'm going to show you the pictures, how they look like, but what exactly are they? So these are just like heat exchanger in that particular room. So what it does is the steam will goes over there and it exchanges it heat to the surrounding air, and the surrounding air gets heated up, and the steam inside the converter condenses, and the condensate will go back to the system. That's what it is pretty much. And the sizes and all that stuff is over here. How are you going to come up with this thing? The capacities are measured with in EDRs. That's what the term that they normally use for the convectors and stuff. What is an EDR? It's just, that's the full form of that one, equivalence of direct radiation. So for every 1 square feet of EDR, you got to have 240 BTUs. That's what it is. And these are the steam traps. So on the convector, I'll show you the picture. Okay, this is how the convectors and radiators look like. So this is a radiator. And over here, as you can see, this mostly the radiators and convectors, they're pretty much the same. The only difference is how the way that they gives the heats off. The radiators, what it does is it gives the heats off using radiant heat, and the convectors by convective heat. That's the difference between these two things. So mostly these are made up of cast iron, and there's this thing in the middle is called fin tube. As you can see, little fins over here. Mostly those are made up of aluminum, and the pipe is made up of copper over here. So which is a very good conductors of heat and all that stuff, where the heat transfer will take place over here. So that's what these are types of the elements. That's the endpoint. You will see these things in appropriate rooms over there, wherever the heat is required and all that stuff. As I said, we normally don't deal with this stuff back home as we don't need heat. But again, it's a very important concept and it's something new to learn too. So these are the traps, and these are the traps. What traps are? As you can see over here, you'll put the trap on the condensate return side. You have the supply side and you have the return side. You'll put the trap over here, which what they do is like they don't let the steam to pass through that stuff into the system. It just vents air from the system so that the steam can't enter, so that the steam can enter and stay. It will hold the steam until its latent heat is removed, which means like it holds the steam in the convector as much as possible, so that all that stuff water that's being condensed back into the condensate water. Remove all the condensate from the forms when the steam condensates. That's what it is pretty much. Again, there are two types of traps. One is thermostatic traps, which you can see it over here. This is an angled trap where it means like the supply is coming from the bottom and this thing is being tied onto the radiator or convected water fin tube, whatever you call it. And this is a strike trap, which means like it's inline. And you have the float and thermo F&T trap. This is simply called as F&T traps, which is a float and thermostatic steam trap. What it does is like, and it has two elements over here, mechanical side and the thermostatic side. The mechanical side, it has a float and a stem. It removes the condensate as it gets over here. So the float will lift and it opens and the condensate goes back into the system, back to the vacuum and condensate pump that we just talked about before, I would say like a few minutes before. And pneumatic system. What is pneumatic system? You'll be having air compressor over there, and that thing is being tied into this. You'll be having these copper lines running throughout the building, right? So you'll be having a thermostat over there. This main line is going to the thermostat. It sets whenever the air pressure is over there, it's going to open up something and it's going to kick. It's going to let the air pass through that stuff into the control valve, and the control valve will open and the steam will pass through. Pretty much it's like you'll set the thermostat, you'll set the temperature at whatever the temperature you want it. Whenever the temperature falls below that particular temperature, it's going to let that air go through and tells the steam valve, tells the control valve to open up to let the steam pass through. That's what it does. It's pneumatic. So again, we don't have enough time, so I can't go deep. So I'm just giving an overview. That's how the schematic is going to look like, the piping and all that stuff. You don't see all this piping exposed. They'll be all concealed in the building. I'm not talking about a small house. I'm talking about like 50-story building or 60-story building. It's huge, huge buildings I'm talking about. So that's how a pneumatic control valve is going to be looking like. So as you can see over here, diaphragms over here, once the pneumatic air tubing is going to be tightened over here, once the thermostat lets the air passes through this thing, it's gonna it's gonna open up the diaphragm and let the steam passes through to the convector, and the latent heat is going to work out that way. So on the DDC system, it's quite opposite. The pneumatic system is the latest system, which is will be having electronic and all that stuff. You'll be having, there won't be any pneumatic tubes running all over there. It's just the control wiring will be running over. So it's a programmable thermostat, and again, you can control it from remotely also, like what. And that's how the control valve is going to be looking like. So it's just the control wiring. What it does is, one of the thermostats tell them to open it up. This motor actuator will open up the valve and the steam will pass through. And once the temperature satisfies in this room, thermostats will say, okay, now we don't want the steam to go through. So it's going to send the signal again. We're going to shut the stuff down. That's it. One more thing to consider is the self-contained control valves. What is self-contained control valve? Now we talked about pneumatic valves and DDC valves, direct digital controls. What are these self-contained valves? For instance, now you don't use this stuff, like you'll just use them in only restrooms, hallways, this and that. They'll hang these elements over here. The element itself is right on the top. There won't be any thermostat in the room or some stuff. So the thermostat itself is on this element over here. Once you set the temperature on this thing, so just to maintain enough temperature, no matter whether the people are there or not, you got to maintain that temperature over there for that space. You will use this kind of things in hallways and restrooms. So pretty much it doesn't need any thermostat. So that itself is the thermostat. Once you set that stuff up to certain temperature, if the temperature falls below that stuff, it's going to let the steam through. And if it satisfies, it's going to close it back. And pretty much that's it. I'm going to wrap up today's session. And thank you for all your time. And I would like to thank Sri Vijay Reddy sir for asking me to do this presentation and to share my insights and thoughts of this stuff with you guys all. And I really hope you enjoyed my session, and just stay safe and be well. It's pretty bad out there. And thank you so much. That'll be it. If you have any questions, you can shoot me, and that'll be it. Let's wrap this thing up.
Thank you, sir.
My pleasure. Thank you.
I request the participants, if you have any question, please, you can interact with the resource person.
ఇక్కడికి రండి డిపార్ట్మెంట్.
I request the participants, if you have any questions, you can interact with the resource person.
Hello.
Yes.
Hello.
Yes. Hello. Yes.
Yes, sir.
Sir, good evening, sir. This is Dr. Uday Kumar from Hyderabad.
Hi. Hi, Uday Kumar. How are you?
Fine, sir. The HVAC design. It is very nice session.
Oh, thank you so much,
this
sir.
session is very quite different from the other sessions. Complete
Exactly.
sessions.
That's why I choose this thing, because it's something new that normally we don't deal back home. So.
It is related to thermal engineering and also heat transfer. So, what is any research scope for this one, sir? HVAC, topic in this one.
Definitely, as I said, since it's COVID thing, right? So the indoor air, that's a very good thing. So we could do a lot of research in that stuff, like how we going to prevent all that stuff. Like we are recirculating the air, right? It's already processed air. You're putting so much of work, you're heating it up or you're cooling it up, and that air is supplied to the rooms, right? And it's being recirculated back into the room. Before coming into that stuff, how you gonna prevent those things? So you could do it on that one. And again, so for the systems, I would say, like, you can come up with like different designs and stuff too. Like, what are the new equipments that you could use? Like, for now, let's take the chiller systems, right? So we can use the chiller system for big facilities, and why can't we use something else? Like, let's take VRF systems. Why can't we put VRFs over there? So maybe we can go and do the research in that scenario, which is variable refrigerant flow systems, which would be maybe less economical and all that stuff. I'm just giving some thoughts, and that's it. So that's how we have to proceed, I would say.
I have one question.
Yes.
Do we have any online tool to estimate the heating and cooling capacity? So instead of taking any large volume, so do you have any?
I'm pretty sure there'll be like tons of software, I would say. Like for instance, right, you talk about carriers, all these manufacturers who are manufacturing the units or HVAC systems like Carrier, let's talk about, and Train, Mitsubishi. I'm not sure about Mitsubishi, but Carrier, they have pretty good system. But I don't think it's a free, it's not a free stuff, but I'm pretty sure it's there. So that's what normally we will deal with, because what these guys will do is they want us to refer, spec'd out their systems while designing the job. So what they do is they will provide all the tools and all that stuff also. But plenty of tools and all that stuff also. But you have to give them the input information like, okay, this thing. So what is the dry bulb temperature, entering temperature, and all that stuff.
So Sivaram sir, please mute yourself. Yeah, sorry.
No, that's fine.
So if I have one more thing.
Yes.
So if there is an, if you're working in an office, we have a different age group persons. So different person will respect with different heating and cooling things.
Yes.
So how you judge the heating and cooling? You would use any thermal cameras, or you just calculate by the?
No, nothing like that. No. That's what it is. ASHRAE comes into picture. ASHRAE says that the comfort zone is going to be set on the. I already showed in one of the slides over there, the maximum and minimum temperatures. What you're going to design, what you're going to come up, what you're going to use in calculating the heating and cooling loads. You'll pick those temperatures. For heating, for instance, it can't be more than 72 degrees Fahrenheit while using the calculations. For the cooling, can't be minimum. It cannot be less than 75. Those are the standards that they put it in. ASHRAE, I think it's ASHRAE 55 who calls for that stuff. So like, for instance, if there are multiple people in the building, right? So in the same room, or for instance, if they're not feeling cold, they can just raise the temperature. That's what it is pretty much. What of the temperature they're comfortable, or they just raise or lower the temperatures they want. But when it comes to the design, those are the requirements. That's what I'm saying. So you can put whatever temperature you want in that room.
I request any participants if you have any interaction.
Yes, sir. Sir, we have a doubt, sir.
Yes, sir. Go ahead.
Hello.
Yes, sir. Go ahead.
I am Dr. G. Nagamaleshwar Rao. Yeah. Sir, in this green engineering systems scenario, how this HVAC controls can be controlled? Any softwares are there to control these HVAC controls?
There are plenty of control systems, like it's called building management systems, which is also called BMS systems. You'll be having Johnson Controls is the major leader in this industry. And you have Honeywell Controls, you have the Siemens. They have their own streams, which is called BMS, building management systems. That's what they do, like integrating all these things automatically. Like you don't have to physically do that stuff, like just setting that programmable. Once you program it, like you can change it with your system or even with your phone. You don't have to be in the building itself. You can be anywhere, like it's remote, everything. So, but that's got to be, the backbone has to be integrated, which means like it's a building management system. That's what they call it.
Yes, sir. Because nowadays we are going for energy efficient systems, isn't it?
Oh, yes.
So that systems, any specific software is there, sir?
For green energies, I would say particular softwares I'm not quite sure of, but like, yes, as I said, like if you go to like Johnson Controls and all, they'll be able to assist you in that stuff. But I'm not quite sure about the softwares and all that stuff in that industry. But definitely there are.
Yeah. Thank you.
You're welcome.
Sir. Thank you, sir. Thank you very much, sir.
Oh, you're most welcome. Thank you, sir.
I request any other participant, if you have a question, please interact with our resource person. Otherwise, we'll proceed further. We will move further. Our HODs are available. Vijay Bhaskar Reddy, doctor.
Sir.
I hand over to you, sir.
Hi, Lepakshi.
How are you, sir?
Fine, Lepakshi.
Yes.
Because I am busy with some meeting, I am unable to I'm unable to attend your thing.
That is
But
fine,
I
sir.
will already it is recorded so that I can go through it.
Got it, sir. Thank you.
So now
Thank you
also
so
the
much.
meeting is there. I want to thank you very much for spending this time
Oh, my
for
pleasure,
giving
sir.
a
My pleasure.
for,
My pleasure.
for
It's all
giving an
mine.
opportunity. So
Sir.
whenever we invited you, you have accepted it. So I'm very thankful to you.
Oh,
Uh,
no, sir. Thank you so
and
much.
we
Yeah, my pleasure, as I said.
request further help also from you whenever we want some
Sure, sir.
latest developments. We
Sure,
request
sure.
so that you please uh, guide us so that because in USA you will be having more advanced things, whereas if it comes to us, it will be little bit late. So that for
Sir.
that purpose, which we are requesting you,
Oh, sure,
and
sir. Sure.
I'm very
Anytime.
thankful for spending you the time. So I will
Oh,
call you back. I will send
sir.
you the mail.
Ah,
Okay.
sir. Thank you. Thank you,
Okay.
sir.
Thank
Thank
you.
you.
Thank you
Thank you,
very
sir.
much. And I
Just stay
thank
safe,
all
sir.
the
Everyone.
sir.
Just stay safe. Everyone.
Yeah. I thank all the participants also for
Thank you, sir.
attending this 6-day international FDP. I think you have enjoyed all these uh, webinars which we have organized, and we are planning to organize in the next week also a different kind of these things. So we will expect to you all to participate in this upcoming webinars or the upcoming FDPs. I'm very thankful because I am in some meeting. I came outside and I am speaking with you. So please, sorry for it. I'm
No,
very
that's
thankful to all
not a
the
problem. Not at
participants.
all. Not at all a problem, sir.
I'm,
No.
I'm very thankful to the participants. And now,
Validate.
Sir,
Moments, madam.
now our uh, coordinators will continue the program. Thank you. Thank you very
Thank you.
much.
Thank
yes.
you.
Thank you, sir. Good evening to one and all. It's my great privilege to give vote of thanks for this 1 week online international faculty development program on research challenges in mechanical engineering from 22nd to 27th of June 2020. I, on behalf of the organizing committee, thank the management for providing us the opportunity to conduct this program. I thank the principal, vice principal, heads of the department for the keen interest and motivation. I thank all the guests who have given their valuable suggestions, ideas, and knowledge for this 6-day program successfully and which are being utilized by the participants internationally. So I thank everybody who has attended, participated from India, Australia, USA, Ethiopia, and Oman countries for your good response on registrations, without whom this program will not be a successful one. I thank all the members of the organizing committee for their effort to make this program a memorable one. Thank you one and all for attending. Thank you.
Thank you, sir. We will conclude today's program.
Oh, thank you so much, sir. And as I
Thank
said,
you.
like, just stay safe, okay? Be well. Everyone, take care.
Thank you, sir. Thank you.
Thanks.
I thank all the participants for being with us. So we'll communicate with further things to your mail and WhatsApp groups also.
Certificates within tomorrow we are going to receive the certificates. Sir. Thank you.
Thank you all.
Yes, sir. Thank you all.
Thank you, sir.
Thank you, sir. Thank you, sir.
Bye bye.
Thank you, sir. Harnath garu.
Thank you, sir. Uday, sir.
Hello.
I will get back to you, sir, personally.
చాలా బాగా చేశారు ప్రోగ్రామ్. ఇట్ ఈస్ కవర్డ్ విత్ ఆల్ ఏరియాస్.
Yes, sir. Yes, sir.
Start with aerospace to the heating and ventilation and cooling.
Yes, sir.
That is HVAC.
Yes.
That is aerospace, air conditioning, and manufacturing. That is a grinding, okay, and MEMS, composites,
Yes, sir.
and metal forming, FEM. So one in NDT, and one is missing with CFD.
Yes, sir.
Because your field is that is thermal engineering, no?
So I'm basically manufacturing, sir.
Acha, manufacturing now. Okay, okay. I am also in manufacturing. That is a metal forming, sheet
Yes,
metal
sir.
forming.
So which college, sir, you work for?
MJIT, Mahatma Gandhi Institute of Technology,
Okay.
Hyderabad.
Okay, so I know, sir. Our Venkatramana garu is IIW welding chapter.
Yeah. He's there. He's my colleague.
I'm also one of the welding chapter member in Hyderabad. This
Okay.
December I completed my PhD from Vellore, sir.
Okay.
VIT Vellore Institute of Technology.
Okay.
Now I joined in SVC Chittur. So
Okay.
recently I moved from Hyderabad to Andhra Pradesh. In Telangana to Andhra.
Hyderabad, ఎక్కడి from
నల్ల
Hyderabad?
నరసింహారెడ్డిలో చేశాను సార్.
అచ్చా నల్ల నరసింహారెడ్డి ఇంజనీరింగ్ కాలేజ్.
మరి శ్రేయాస్ ఇంజనీరింగ్ కాలేజీలో డాక్టర్ సురేష్ అఖిల గారితో పాటు రీసెర్చ్ కంటిన్యూ చేశాను.
గైడ్ ఎవరు?
డాక్టర్ సురేష్ అఖిల వచ్చి అడ్వైజర్ సార్, రీసెర్చ్ అడ్వైజర్ అవుతారు. అంటే విఐటి కో గైడ్ యాక్సెప్ట్ చేయదు.
అవునవును. ఓకే.
మెయిన్ గైడ్ వచ్చేసి డాక్టర్ ఎడిసన్ గారు అని మన తెలుగు అతనే.
ఓకే.
అక్కడ ఫ్యాకల్టీ ఉన్నా థర్మల్ లో నాది ఇన్ఫ్రారెడ్ థర్మోగ్రఫీ మీద టెంపరేచర్స్ మెజర్ చేసి దాని రెసిడ్యూయల్ సిమ్యులేషన్ ఎక్స్పెరిమెంటల్ చేసి.
ఓకే. ఇప్పుడు ఇక్కడ SV8 లో చేస్తున్నారా? ఓకే.
అవును సార్.
ఓకే. హైదరాబాద్ వచ్చారా వెల్డింగ్ దానికి ప్రోగ్రామ్స్ కి?
ఐ వాస్ దేర్ సార్ ఫర్ ఆల్ ద ఈవెంట్స్.
నేను కూడా అటెండ్ అయ్యానా? ఓకే. నైస్. అదే ఎక్కడ చూసినట్టు కనిపిస్తుంది కానీ ఓకే. నేను కూడా శ్రేయాస్కి వెళ్ళాను 2-3 సార్లు. ప్రాజెక్ట్ ఎంటెక్ ప్రాజెక్ట్ వైవాస్.
ఓకే.
చంద్రశేఖర్ ఈజ్ మై క్లాస్మేట్.
ఓకే.
చంద్రశేఖర్ ఈజ్ HOD, ఫాస్ట్ HOD.
ACS రెడ్డి. చంద్రశేఖర్ మేము గుర్తుపట్టలేము, ACS అంటే గుర్తుపడదు.
ఓకే. మాకు చంద్రశేఖర్ అని పిలుస్తాం. ఈజ్ మై ఎంటెక్ క్లాస్మేట్.
ఓకే సార్.
I did two MTechs now.
Oh yes sir.
One MTech with SVU, one other MTech with JNT.
Yes sir.
JNT classmates.
ఓకే. సార్ కూడా సబ్మిట్ చేశారు సార్ ఇప్పుడు?
చేశాడు మొన్న 1 week బ్యాక్ చేశాడు.
అదే కాంటాక్ట్ లో ఉంటాం, రెగ్యులర్ గానే ఉంటాం.
నేను కూడా కాంటాక్ట్ మొన్న చెప్పాను నాకు.
అవునా? ఓకే.
వీఆర్ ఇన్ కాంటాక్ట్ ఓన్లీ, ఎందుకంటే సేమ్ ఏరియా ఈజ్ ఆల్సో ఫార్మింగ్.
ఓకే. మీ పేపర్స్ లో ఆయన పేరు ఒకసారి చూసినట్టు గుర్తు నాకు.
నేను కూడా అదే ఫార్మింగ్ లో చేసుకున్నాను. మాది ఎప్పుడు నియర్లీ 2012 ఇస్ కంప్లీట్.
అదే 10 years. ఓకే.
టచ్ లోనే ఉంటాడు. కావాలని కూడా అడుగుతాడు ఇన్ఫర్మేషన్ అది ఇది. మొన్ననే సబ్మిట్ చేశాడు.
అదే సార్. చాలా స్ట్రగుల్ చేశారు బాబు.
ఇక స్ట్రగుల్ అంటే ఇక ప్రైవేట్ కాలేజీలో తప్పదు కదా సార్. ఏం ఫెసిలిటీస్ ఉండవు, చేయమంటారు. లక్కీ ఆయనే ఫెసిలిటీస్ క్రియేట్ చేసుకున్నాడు. దట్ ఈస్ అ గ్రేట్ థింగ్.
ప్రతి ఒక్కటి సార్ 0 నుంచి స్టార్ట్ చేసి 100 రీచ్ అయ్యాడు.
అదే నేను కూడా వెళ్ళాను, ఒకసారి చూపించాడు వాళ్ళు ఎంటెక్ వాళ్ళకి వెళ్ళినప్పుడు. సో టచ్ లో మన PhD సబ్మిషన్ అంత వరకు టచ్ లోనే ఉన్నాడు. కొంచెం బూస్ట్ అప్ కూడా ఇచ్చాము, ఎట్లా చేయాలి ఏంటి అదంతగా. సో సబ్మిషన్ అయిపోయింది. అదే ఇక అయిపోతే ఇంకా 1 year లో అయిపోతుంది ప్రాజెక్ట్. ఎందుకంటే ఈ వాంట్స్ టు దట్ డిగ్రీ ఇస్ మ్యాండేటరీ ఫర్ హిమ్.
Yes sir.
Because he has completed all the posts.
Yes sir. అవును సార్. అదొకటి మిగిలేదు.
లెక్చరర్, అసిస్టెంట్ ప్రొఫెసర్, అసోసియేట్ ప్రొఫెసర్, HOD, వైస్ ప్రిన్సిపల్ ఆల్సో.
నరసింహ
ప్రిన్సిపల్ చేశాడు, వైస్ ప్రిన్సిపల్, సమ్ HOD, ఆ స్టేజ్ దాకా వెళ్ళాడు. సో ఈ వాంట్స్ టు దట్ డిగ్రీ ఇస్ మ్యాండేటరీ. చెప్తూనే ఉంటాడు మాకి, నీకు అది డిగ్రీ కావాలి కంపల్సరీ అని చెప్పామన్నమాట. మా స్టూడెంట్ కూడా పంపించాం ఆయన దగ్గరికి, అదే రీసెర్చ్ వర్క్ గురించి ఎక్స్ప్లెయిన్ చేసుకోవడానికి అని. ఫెసిలిటీస్ ఇచ్చారు. సమ్ ఏదో ప్రాబ్లం ఉంది, రిపేర్ చేయాలన్నారు, కరోనా వచ్చేసింది.
ఓకే. అప్పుడు నాతో అన్నారు సార్, మీరు పొద్దున్న సార్తో మాట్లాడేది కూడా ఇంతకుముందు అన్నారు, మనం ఏదైనా 2 metals వెల్డ్ చేసి దాన్ని డీప్ డ్రాయింగ్ చేసి చేద్దాము. అంటే వెల్డింగ్ లో నేను ఉన్నాను కదా, మీ ఇన్పుట్ పనికి వస్తుందని అడిగారు సార్.
అది ఒక వేరే స్టూడెంట్ చేస్తున్నాడు, అది ఫార్మింగ్ అవ్వట్లేదు సార్. అది అది పంచి ప్రెస్ అవ్వగానే ఇమ్మీడియట్‌గా బ్రేక్ అవుతుంది అనమాట.
ఓకే. ఓకే.
నేనేం చేశాను, దాన్ని మామూలుగా అన్ని ప్రాపర్టీస్ డిసిమిలర్ మెటల్ వెల్స్ జాయిన్ చేసి టెన్సైల్ స్ట్రెస్‌ని కట్ చేశాం.
ఓకే.
విత్ వర్టికల్ వెల్ అండ్ విత్ హారిజాంటల్ వెల్. విత్ ఆల్ ఓరియంటేషన్ 0 degrees, 45 degrees, 90 degrees తోని. చేసి అయనైజేటబుల్ ఫ్యాక్టర్ అవన్నీ ఫైండ్ అవుట్ చేసాం. స్ట్రెయిన్ హార్డనింగ్ ఎక్స్‌పోనెంట్స్, గ్రాఫ్‌లు అన్నీ గీసాము. చేస్తే వీఆర్ గెటింగ్ వెరీ లెస్ వాల్యూస్. హౌ కెన్ వి justify that one? That justification is very difficult.
Yes, sir.
We did the simulation also. Simulation is the same.
సిమ్యులేషన్ నాకు సాఫ్ట్వేర్ కూడా నేర్పిస్తా అని చెప్పారు సార్.
సిమ్యులేషన్
నేను డౌన్లోడ్ చేయించి ఈఎస్ఐ గ్రూప్ ఏదో ఉంటది.
అదే వస్తున్నాయి. అదే వస్తుంటే ఒకసారి ఏం చేసాం, వై స్ట్రెంత్ ఇది లెసన్ జస్ట్ టేబుల్ మీద ఊరికే కింద పడింది. టేబుల్ మీద పెట్టాం అన్ని స్పెసిమెన్లు, కింద పడి ఊరికే బ్రేక్ అయిపోయింది ఆటోమేటిక్గా. సో అప్పటి నుండి వీఆర్ థింకింగ్ ఫర్ రెక్టిఫికేషన్ ఆఫ్ దట్ ప్రాబ్లం.
ఓకే.
స్ట్రెంత్ ఉండట్లేదు సార్. టిగ్లో అవ్వలేదు, మిగ్లో అవ్వలేదు, ఆర్క్ వెల్లింగ్ కూడా అవ్వలేదు.
అది 3 హై హీట్ కదా సార్ ఇది.
చేసాం 2 mm వరకు చేసాం. 1 mm, 1.5, 2 mm వరకు చేసాం టిగ్లో, కానీ కాలేదు. తర్వాత మళ్ళీ ఎఫ్ఎస్టీలో చేసాము. ఎఫ్ఎస్టీలు అయినాయి, వెల్డ్ అయినాయి. ఎఫ్ఎస్టీలో
ఇది లేజర్స్ లో పల్స్డ్ మోడ్ అని ఉంటుంది సార్.
చాలా స్లోగా చేయాలని ఇది కరిగిపోతుంది సార్ ఇమ్మీడియట్ గా. అల్యూమినియం
వాళ్ళు ఇప్పుడు నేను లేజర్ లో చేస్తున్నాను.
ఓకే.
విత్ ఇన్ 5 seconds లో 100 mm ప్లేట్ వెల్డ్ అయిపోతుంది.
అయితే అంతవరకు చేసాము. మళ్ళీ తర్వాత ఇక డిఫార్మేషన్ ఫార్మింగ్ చేయాలంటే ఆ సర్క్యులర్ బ్లాంక్స్ కట్ చేసాము. వీ కెన్ గో ఫర్ ఇన్ ద ప్రెస్. హైడ్రాలిక్ ప్రెస్ లో పెట్టగానే అది పంచి డ్రా చేయగానే బ్రేక్ అయిపోతుంది ఇట్లా. అది వెల్డ్ దగ్గరనే జాయింట్ బ్రేక్ అయిపోతుంది. అక్కడ బ్రేక్ అవ్వకూడదు కదా. ఇక్కడ అది ఎందుకు బ్రేక్ అవుతుంది అనేసి వీఆర్ సర్చింగ్.
హీట్ ఉంటుంది సార్, ఒకటే వచ్చి మెయిన్ హై హీట్.
అదే ఇందాక సార్ చెప్పారు కదా హీట్ ట్రీట్మెంట్ చేయించాలని. ఇందాక ఒకసారి హీట్ ట్రీట్మెంట్ చెప్పారు కదా.
ఇది ఉంటుంది సార్
మార్నింగ్ సార్. హీట్ ట్రీట్మెంట్ చేయించని చెప్పాడు కదా.
హీట్ చేసి ఇంకా హీట్ ఇన్పుట్ తగ్గిపోతుంది. అదొకటి. లేకపోతే లోకలైజ్డ్ హీట్ అని మనం చేసుకోవచ్చు.
అది మళ్ళీ ఇప్పుడు మనం ఎలివేటెడ్ టెంపరేచర్ దగ్గర అవుతుందేమో చూడాలమ్మా. మేము రూమ్ టెంపరేచర్ దగ్గర తీస్తున్నాము. ఎలివేటెడ్ టెంపరేచర్ దగ్గర అవుతుందేమో చూడాలి. ఎందుకంటే బట్ ఎలివేటెడ్ టెంపరేచర్ దగ్గర ద స్ట్రెంత్ విల్ బి లూజనింగ్ కదా ఫర్ ద టెంపరేచర్స్. అదొకటి. ఎందుకంటే అల్యూమినియం ఎస్ఎస్ ఇట్ ఇస్ నాట్ టు బి వెల్డబుల్.
మేము సిమ్యులేషన్ ట్రై చేసాం సార్. అది ఒకటి ఇక్కడ మన పార్టిసిపెంట్ కృష్ణ చైతన్య ఉన్నాడు. అతను ఎంటెక్ దాని మీద చేశాడు, ఎపాకస్ మీద చేశాడు.
ఓకే. ఓకే.
దానికి ఇనిషియల్ టెంపరేచర్ ఏదో మార్చి మేము అది హీట్ ఇది అవ్వట్లేదు.
ఓకే. ఓకే.
ఇనిషియల్ టెంపరేచర్ అదే సిమ్యులేషన్ ట్రై చేసాం, హౌ ఎట్లా ఎస్టాబ్లిష్ చేయొచ్చు అని.
సిమ్యులేషన్ లో ఎట్లా కింద మీద పడి ఏదో చేయొచ్చు, కానీ షుడ్ నాట్ బి పాసిబుల్ విత్ ఎక్స్పెరిమెంటల్. ఎందుకంటే ఎక్స్పెరిమెంటల్ ఇస్ స్టాండర్డ్.
నేను పర్సనల్ కాల్ చేస్తాను సార్ మీకు.
ఓకే. 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 రైట్ సార్. రైట్. నైస్.
హెచ్ఓడి సార్ కాల్ చేస్తాను.
రైట్ సార్. రైట్.
థాంక్యూ సార్.
Shall I leave?
Yes sir, you can leave.
Okay, right. Thank you.
Thank you all the participants for being with us all the 6 days.